Welcome to this explainer. Today, we are diving straight into the hardcore engineering behind API Specification 5L. If you've ever looked at a massive industrial pipeline and wondered about the exact metallurgical rules keeping it from failing under immense stress, well, you're in the right place. We are unpacking the exact life-saving math that stands between stable energy transport and total structural failure.
Picture this, a high-pressure pipeline failing and literally unzipping like a jacket across miles of terrain, or just dissolving from the inside out. Terrifying, right? So how do you stop a line from tearing open at the speed of sound? That single high-stakes question is exactly what drives the API 5L standard, making these engineering guidelines absolutely critical for infrastructure safety. To make this incredibly dense standard digestible, we've structured this explainer into 6 logical parts: preventing catastrophic failures, stopping fractures with Annex G, 5 approaches to toughness, surviving sour service with Annex H, testing for toxic environments, and finally, the future of pipeline integrity. Let's get right into it.
Part 1, preventing catastrophic failures and the real stakes of API 5L.
Why do we need such obsessive rules for steel in the first place? Well, the baseline problem is actually pretty straightforward. If you try to use standard run-of-the-mill pipe to transport extreme energy, it's a recipe for disaster. Pushing high-pressure gases and toxic fluids across continents subjects the metal to intense forces that basic steel simply wasn't forged to handle, leading to rapid structural failure.
Moving on to part 2, stopping fractures. Specifically, we're looking at Annex G and how to arrest the dreaded zipper effect. Annex G is a massive component of API 5L entirely focused on stopping physical pressure fractures in their tracks. And the absolute key concept here, CVN-absorbed energy, or Charpy V-notch testing. Think of it as a measurement of the pipe's pure toughness. It tells engineers the exact amount of energy the steel can absorb from a sudden, massive impact without splitting wide open. When a crack starts, the steel itself has to absorb the energy to stop it from traveling down the line. So, how do engineers actually use this? They look at Table G.1. It's essentially a massive matrix. You cross-reference the pipe's outside diameter with its specific steel grade, say an X70 or an X80 pipe. Boom, you find your exact minimum CVN energy, in joules, required to stop a fracture cold at a specific design pressure. It's just pure calculated safety. Which brings us to part 3, 5 approaches to toughness, and calculating those limits.
Now, you and I both know that no two pipelines are exactly alike, right? Operating at different temperatures, pressures, and terrains means you need options. So the standard gives engineers these 5 distinct methodologies to calculate that required toughness. As you can see, they range from straightforward EPRG guidelines for basic lean gases all the way up to extreme real-world physical testing.
The really fascinating part is how the standard dictates exactly when you have to scale up your math. Take approach 2, the Batel's simplified equation. Perfect for standard natural gas with single-phase decompression up to 7.0 megapascals. But if you're dealing with rich gases, hitting a 2-phase decompression boundary at higher pressures, like up to 12.0 megapascals, you are legally required to step up to approach 3, the much heavier, more complex Batel 2-curve method. But hey, what happens when theoretical math simply isn't enough? Enter approach 5. When the math gets too uncertain, engineers literally blow up a section of the pipeline in a controlled environment. They match the exact gas composition, temperature, and pressure levels, and just burst it. It's the ultimate, undeniable physical proof that the steel can actually arrest a fracture. All right, part 4, surviving sour service. This is Annex H, where we fight the invisible enemy. We are pivoting now from explosive physical pressure to downright chemical warfare inside the pipe. And API 5L does not mess around here. Look at this explicit warning right out of the gate. Standard PSL1 pipe is absolutely not suitable for sour service, period. It will utterly fail when exposed to these chemicals. If you are operating here, an upgrade is mandatory. So, what makes sour service so incredibly dangerous? We're talking about environments heavily contaminated with highly toxic hydrogen sulfide, or H2S. It acts as an invisible enemy. The hydrogen atoms are literally small enough to slip right into the molecular structure of the steel. They make it brittle, causing it to secretly crack from the inside out, a nightmare known as hydrogen-induced cracking. This is exactly why Annex H is so strictly enforced.
To fight this microscopic attack, metallurgists actually have to change the fundamental recipe of the steel itself. Table H.1 enforces severe limits on specific elements during manufacturing. For example, they clamp down hard on sulfur and phosphorus. Keeping sulfur incredibly low, sometimes down to just 0.002%, prevents the steel from forming inclusions that act like a sponge for those deadly hydrogen cracks. Moving to Part 5, testing for toxic environments and proving that pipeline resilience. Mixing the perfect steel in the furnace just isn't enough. Manufacturers have to relentlessly prove the pipe works before it ever goes into the ground. These 3 mandatory tests are the holy trinity of sour service quality control. First, evaluating for that hydrogen-induced cracking. Second, strict hardness limits. Steel simply cannot exceed 250 on the Vickers scale, because if it's too hard, it's dangerously brittle. And third, sulfide stress cracking testing, to guarantee the pipe won't suddenly shatter under tension. And Table H3 guarantees these tests actually happen on a rigorous schedule. We aren't talking about casually checking one pipe a month. Depending on the class of service, these inspections must be performed per heat of steel or per specific length of pipe. It is an aggressive, relentless process to make absolutely sure 0 microscopic defects slip through to the field. And finally, Part 6, the future of pipeline integrity and how we adapt for tomorrow. API 5L isn't just stuck in the past with traditional oil and gas. It is actively shaping the future. With the massive global push toward carbon capture and storage, Annex G is evolving to deal with transporting volatile carbon dioxide. Because CO2 behaves totally differently than natural gas under decompression, the standard now actively segregates the rules, requiring distinct guidance for gas phase CO2 versus denser than gas phase CO2. In fact, when you're dealing with extremely dense CO2, the standard basically holds its hands up and acknowledges the limits of our current mathematical theory. It explicitly mandates that specialist advice must be sought, and only approach 5, that full-scale physical burst testing, is permitted. The environment is just so new and volatile that only a literal explosion can prove the design is safe. Which leaves us with a pretty wild thought to wrap up this explainer. As our global energy demands push infrastructure to the absolute brink, asking it to transport next-gen fuels, captured carbon, and just unprecedented pressures, how much further can these engineering standards push the literal laws of physics before we have to invent entirely new materials? It's definitely something to think about the next time you see a pipeline stretching across the horizon. Thanks for joining me on this one.